what are your benchmarks towards accomplishing that goal, and how far off in time are we looking here? Are we looking a decade, 2 decades? And which are the short-term goals that we need to meet so that we know that we're making progress?
Okay. So some of the results that we've achieved so far is that we've put together a roadmap that contains information about what is required to do a substrate independent mind, which are the different routes that you can take. There are a few major routes that you can approach it by. What projects or what sort of projects would provide the tools necessary to fulfill the requirements of any one of those particular routes, and then to connect with that the people who are working in those areas and to discover key pieces that are missing, parts that nobody's really paying enough attention to, and what needs to be done there. In the last year, there's been an increasing interest from high-profile people in neuroscience, such as Ed Boyden, to also look into brain circuitry and how would you replicate it and how would you acquire the data for that. And so we have started some early collaborations on developing technology that can actually acquire data at large scale and high resolution. And it looks like this is giving us a very good picture, at least along one of the directions towards substrate independent minds, namely the whole brain emulation approach, this very conservative approach, and what it needs in terms of structure and in terms of function, and then tools that can acquire the structure and tools that can acquire the functional characterization of components. So this is very clear, and that gives us a really concrete project for whole brain emulation, at least for that approach to substrate independent minds. As far as milestones are concerned, we're still finishing up some of the fundamental literature so that we can put that out early in 2012. Then along 2012, I think it's time to do the first projects on the large-scale data acquisition from the functional characterization, for the functional characterization of components, because that part's been neglected somewhat. That's basically one of those key areas that needed more attention. Meanwhile, to also support the ongoing work by people like Ken Hayworth, who've been doing the structural side of things. And then hopefully after 2012, we should at least have a very early prototype that shows that the kind of tools we need are available in both of those parts, so structural and functional. And the hope is that knowing that and being able to demonstrate that it will spur the kind of investment that's necessary to build these on the scale and with the kind of precision that's necessary to get so much data, to get all this data that you would need out of a brain. Now, how long will that take to get to that final result? That's a really hard question, because it depends so much on the resources that you get. It depends so much on how much people invest and whether they, really put a lot of people on the job, or if a lot of scientists pick it up. So yeah, I've tried to display this on a graph that I showed during my H+ talk in Hong Kong recently, and it was a quick graph just to show that the connection between resources and when would it get done. And so I always hope that people will put in so many resources that it can get done within the next 20 years. But maybe I'm being optimistic, maybe not. We'll have to see. It's also therefore a matter of advocacy. It's a matter of telling people, look, this is a concrete project. This is not like, let's say you want to try life extension and you want to do it the biological route, and then very often somewhere someone says, oh, and to do this, we have to understand biology. They just kind of say that, understand biology. It's like, oh, wow, but that's a really big topic. Or even if you had a topic where it said we have to understand neuroscience, that would be really huge. But this isn't, because whole brain emulation is really conservative. It says we're assuming here that what we are is an emergent function of what's going on at the bottom level. And the bottom level we've studied for many years. We know, even though we don't have catalogs of everything that's there, we know how to get that data if we need it. We know that if we need a parameter about a certain type of synaptic channel, we know what kinds of tests to do to acquire that data. So what we need now are tools that can do this at large scale and high resolution. So it's a matter of applying our knowledge, our scientific knowledge about how neuroscience works at that level today, together with the engineering that is required to build the kinds of tools that can get that data. It's a data acquisition problem. It's not a huge scientific problem. It's not a maintenance problem. It's not how do you keep this car running forever or something like that. in that sense, it's very concrete, and it's about how many resources.
So let me ask you about the detail to get a little bit deeper about what we do and what we don't know. Let's take me, for example, and let's see if this question will be outside of your field, but I suffer from migraine occasionally, and on some occasions it's pretty serious. So I've been to the doctor a couple of times. We've done fMRI scans and a couple of other tests, and so far they're clueless. They have no idea what could be the reason. One theory was that I might have sinusitis, which turns out I don't. My eye prescription is accurate because I wear contact lenses, but I get the headaches not when I have my contacts off, but when I have them on too. Therefore, that's not related to that either. And the fMRI did not seem to help them in any way possible to come up with a diagnosis. So let me ask you this: doesn't that show that we're very, very far away from any practical results? One, and two is, what would be the dream outcome of us getting to know pretty much everything that there is to know about the issues and the problems and the neuroscience that's happening right here?
Yeah. I think that's another point that really needs to be made very clearly. One thing is to want to understand the brain fully. The other one is whole brain emulation. They're not the same thing. Even if you make an emulation of a brain, a complete emulation from the ground up, and even if it works, it doesn't mean that you have a complete understanding of the brain. Not automatically. It will make it a lot easier to get that understanding because at least you have total access to every component while it's functioning, and you can see what's going on, and you can turn it off and turn it on, test, does changing this change anything? So it will allow exploration in a way that we've never been able to do before. I like to call the idea a virtual brain laboratory in a sense, and everything can be backed out of. So instead of trying a drug on some people and saying, well, let's see if it has any adverse reactions, if it does have adverse reactions, you can dial it back. So those are huge advantages if you're going to do any kind of medical research, if you're going to do scientific experimentation, but it's not an automatic outcome. Because as I was saying before, there's a difference between this low-level understanding and giving that answer, yes, we understand the brain. We know at every hierarchical level how this strategy works. And you're right, there's a big difference there. But I see those kinds of things, like being able to use it as a virtual brain laboratory, also as some of the huge advantages if you make these kinds of models. And that doesn't just happen when you're doing whole brain emulation on an individual level for a person because they want that. But also if you're just doing brain emulation, brain circuitry emulation of, say, regions of the brain or of animals, smaller animals where you can test things. This is some of the reasons why many of the neuroscientists who are now coming on board with the really exciting human connectome project, so this idea of getting all the connections from the brain, and brain emulation, so brain circuitry reproduction, like the kind of things that Ed Boyden's interested in, they're coming on board because they know that that is what we need now. We're done just looking at very small scale stuff at high resolution or taking fMRI scans where all you can say, oh, yeah, there's activity in that part of your brain when you're thinking this, but what does that really explain, right? Okay, so it had to happen somewhere, right? The activity had to be somewhere. You need that connection between the two, and that means you need to do the kind of detail that you're usually doing at the low level, but at a very large scale. The kinds of populations of neurons that are actually involved with these kinds of functions in the brain.
So in a way, the whole brain emulation will be a step towards the basically a step in the direction of learning more about the brain itself and diminishing that area that we don't know what's going on.
It would certainly help, yes. Yeah.